Hi there, Mr. Lee here. In this video, we are going to go over the force of friction. Alright, so we're going to go over what causes friction, the formula, and different misconceptions. Okay, so a quick overview on what we know about the force of friction so far. We know that the force of friction is a force that always goes against motion. Okay, and usually it just slows down a object, but we're going to dive into that a little bit more. All right, so what causes friction? Let's zoom in on this. So when we have two surfaces, so the first thing that we need to know is that there are always going to be two surfaces. Okay, you need two surfaces for friction to exist. If we were to zoom in on a surface, so let's say we have a textbook and that textbook is on top of a desk. All right, so I have a textbook right there and I have a desk right below it. So in this scenario, if we were to zoom in right there, okay, on the surface of the textbook, we would see these like mountains and like these ridges, and like it would look like the Grand Canyon and like the Himalayas and like all the Andes mountains, right? It's just like this mountainous. There's crags, there's cracks, and there's like valleys. Okay, even though on a macro scale, like according to our eyes, and we look at the textbook, we're like, oh, that's a pretty smooth textbook. Okay, and if we also zoom in on the surface of the table, okay, we also zoom in on the surface table. Guess what we'll see? That's right, we'll see those mountains and those crags and those valleys and those divots and those spikes. All right, so what causes friction? Now, remember what we discussed earlier. Friction is there when there's a reason for motion. Okay, it always goes against motion. So when you have like a textbook and a surface of like a desk and they're on top of each other, and you move the book, right, and you move the book back and forth, right, and you can, well, if I do this with my hand, I feel it, but the mountains and the crags and the valleys, they're like constantly rubbing against each other, and they're like impacting each other and running into each other, and that's happening on a very small microscopic, sub-microscopic scale. And the bashing of the surfaces is what causes friction. It's really cool. Now that's what it is in a grand scheme, but how does it really apply to us here? For the physics class. So we're going to take a look into the formula. All right, so the formula of the force of friction is equal to, so force of friction is equal to mu, aka the coefficient of friction, and we'll go into that a little bit more, times the normal force. Right, so we know about the normal force, but what is this? What is this? What is this U with a tail? Okay. By the way, that's how you draw it, right? You write a U, but it kind of has like a tail, or it kind of looks like an M that's like drooping on the left side. Mu. Okay. So let's go over this. Mu is a Greek letter, and we call it the coefficient of friction. Okay, it is the coefficient of friction. And a lot of things in physics, the definition comes from the equation. So the equation for mu is, and I'm getting this from the force of friction equation, I'm just dividing both sides by the normal force. That is the definition, aka the equation for the coefficient of friction. It is the ratio of the force of friction between two objects, two surfaces, and the normal force of one of those objects. Okay, but you're like, all right, but like, what does it actually mean? All right, so what it means is that if you have two surfaces, the mu tells us how much friction can be produced between those two surfaces. All right, so a good idea to think about is, let's say you have boots, like you have rubber boots and you're walking. All right, so let's do this scenario right here. So we have a sidewalk, right? And this is me, hello, having a good time. It's outside, right? I'm walking and I have my shoes on, my rubber boots. Okay, so the mu in this scenario will be the rubber and the sidewalk. Okay, and when I'm like walking, right, my feet are moving. Okay, my feet are moving backwards. So between the rubber and the sidewalk, we have this value mu, this coefficient of friction, and it's a predetermined value, right? like material scientists and these engineers, they have this giant table full of these values for mu. And so for our case, we'll just come up with something here. Let's say it's like 0.7. Okay, 0.7. By the way, mu does not have any units. It's our first unitless value or variable. No units at all. And that's because if we take a look over here, we have newtons divided by newtons, and the newtons, they just simply cancel out. There's no variables for mu. All right, so I'm walking, rubber on sidewalk. That's, there's a lot of friction there. If there wasn't, I'd be slipping, sliding everywhere. And then it's February, and it's cold outside, and boom, right there, there's an ice patch. Okay, so I'm going to be walking on the ice patch. Oh my goodness. And I'm not careful. Okay, you hear me? I'm not careful when I'm walking on this ice patch. I'm like, I'm dangerous. I'm just going to walk on this ice patch and I don't care what happens to me. Okay, so the moment I step on the ice patch, my mu has changed. My coefficient of friction has changed. So instead of rubber on sidewalk, it is now rubber on ice. Okay, rubber on ice. So now let's go back to our idea of what creates friction, right? On this like atomic scale, all these like rough surfaces. So if I were to take a look at my rubber soles, on the bottom of my soles, it's pretty like rough, right? If I were to zoom in, there will be all these mountains and these crags and these valleys. There will be everywhere. And same with the sidewalk. Like visually on a macro scale, so macro just means on like we don't need any tools to enhance our vision. We just look at the sidewalk and we're like, wow, that's a pretty rough surface, right? We see all these mountains and valleys and these crags, and we see it. And so like between those two mountains and valleys, and when they're like crushing against each other, it creates a lot of friction. But ice is relatively smooth according to our eyes, but even on the macro scale, and when we zoom in, it's not as rough as the sidewalk. So there's less of these mountains and these valleys, and there's less gnashing of these surfaces. And so we can say that the mu, the ratio between rubber and ice, is lower. Let's say it's like, I don't know, 0.2, okay? It's a lot lower. Therefore, the force of friction that will be created between the rubber shoes and the ice would be smaller. The force of friction will be smaller compared to my rubber shoes on the sidewalk. And inevitably, I would slip, right? Or I will fall. Because that's how ice and walking on ice works. So that's mu. Now, in order to really determine mu, there is a lab that scientists do, and we will in class do a simulation of this lab. You would get a object, and you would drag that object across a surface. Okay, so here's my surface, okay, and we would attach like a rope or a string to this object, and attached to that string, we would have this thing called a force meter or a force probe, right? And what that tells us is just the amount of newtons being exerted, or the amount of force that is being exerted. Okay. A very common force meter is your bathroom scale, right? If you step on the bathroom scale, your force of gravity down is being read by that scale, and it tells you, your weight. And if you were to convert it to newtons, you would know your weight in newtons. And so that's what it does. It just tells you the force. And so this is something cool. So when we're doing this, right, we take the force probe and we pull on the force probe, and we pull on the object that's on the surface, right? And then you're instructed to pull very carefully, very carefully. And you can try this right now if you have like a heavier object around. If you push on that object very lightly, very carefully, the object doesn't move. Okay, and then you increase your force. You increase your force a little bit at a time, and a little bit at a time, and a little bit of time, until eventually you're pushing or you're pulling hard enough so that the object moves. All right, so that's what's going to happen with our lab here. You're going to be pulling very carefully until the object eventually moves. And then the force probe, if we were to collect that data, it will look something like this. So the y-axis is force, and the x-axis will be time, right? And so see what I do here, right? We're pulling very carefully. We're pulling very carefully. We're pulling very carefully. Now, all this time, the object is not moving, and then all of a sudden, the object starts to move. And then our data would be a little bit more like this, a little bit more flat. Okay, so I want to point out a couple of things here. There's very important ideas that's going on here. There's actually two types of friction. What? Yeah, there's two types of friction. The first type of friction is what we call static friction. Or, whoa, I'm going to call that F of Fs. Force of friction, static. Now here's a vocabulary term for you. Static, unlike the electricity stuff, static means not moving. Okay, so along this this diagonal line, we have what we call static friction. So the object's not moving. But you might be thinking to yourself, wait a minute, Mr. Lee, I thought you said that friction can only exist if objects are moving. Well, the object would be moving if there was no friction, right? So if you're pulling the object would be moving, but the force of friction is preventing that motion. It's going against that motion, all right? And so we pull until we get to this part right here. Right there, that's very important. This is what we call the force of friction static. This is the max. And at that point, that is the exact moment when the object will start to move. And then we get down here, this is what we call force of friction kinetic. Okay, that K stands for kinetic, and kinetic means motion. Okay, kinetic means motion. And you'll notice that the force of friction kinetic, it's a constant value. That does not change. But the force of friction static, okay, it constantly changes up until a point. All right, and if we were to do, like, if I were to ask you, what are the two values for mu? Because we're able to do that. Because now I'm telling you right now, there's two different values for mu for the different surfaces. So in order to calculate mu, right, we would see what this value would be, F of Fs, right there. Okay, and we would put that into our equation, mu sub s times the normal force. We will put in whatever value we have there in for force of friction static. We will put it the normal force for our object, and we can find the force of, the coefficient of friction static. The coefficient of static friction. Static coefficient. There we go. All right. And here we can find if we take a look at this value for the force of friction kinetic, right? We can use this equation, mu k. All right, we will put in whatever value is right there for the force of friction kinetic. We will put in whatever we have for the normal force in order to find the coefficient of kinetic friction right there, mu k. That's what we will find. Okay, and there are two different values. Now here's what's important. If we're using the same object, and the same object will have the same normal force, okay, and we know that the force of friction static is greater than the force of friction kinetic, we can say that the coefficient of static friction is greater compared to the coefficient of kinetic friction. And this is a universal truth that mu sub s is always greater than mu sub k. Okay, and therefore f of s is always going to be greater than f of k. All right? Yeah. Now you might be wondering why. Why is this the case? So simply put, if we have an object on top of another object, we're gonna go back to this idea here. This is why we started off with this idea. Okay, if we have two objects on top of each other, okay, and they're canyons and they're mountains, they're all the ridges, they're all locked into place, and you're trying to move it, you're trying to budge it, it's not budging, and that's because everything is kind of like locked into place. Okay, and like just imagine if you're trying to like push like a refrigerator all by yourself. You're pushing on the refrigerator, it's pretty heavy. Well, you shouldn't be pushing on the refrigerator in the first place, but you're trying, and it's just not moving. Okay, but you push and you push and you push, and eventually you get to a moment where all this ridges and there's locks, like you push enough so that it'll start to slide. Okay, once it's sliding, the mountains and the ridges, they don't have enough time to really like lock into place. And so the force of friction kinetic is a lot lower because there's like, it's just constant scraping at that point. There's nothing being locked into place. And so when you're pushing on the refrigerator, you'll notice that when you're pushing on the refrigerator and it's moving, it's so much easier to move. And that's because the mu k is lower than the mu s. All right, so here's something cool. We're taking a look at this equation, the force of friction equation, and we looked at how mu affects things. Okay, there's two different types of mu's. Now let's take a look at how normal force affects things. Okay, so I'm going to go over a couple of different scenarios. I'm going to do this over on the other side. So let's say you have a dresser, right? You have a dresser, and in this dresser you have clothes, and you want to move this dresser. Okay, you want to move this dresser, and on the bottom of the dresser, I don't know, you have these nubs there, right? And it's, let's say, plastic, and you have carpet. Okay, you have carpet flooring, and you're trying to move this dresser across the floor. Okay, and you're pushing on the dresser, and it's just not moving because your force of friction is way too big, and so you come up with a brilliant idea. You're like, this will be so much easier to move if there's nothing in the dresser. And your reasoning is, well, because there's less in it. Well, yeah, of course. But the force of friction equation also comes into place, right? So F of F is equal to mu times the normal force. Now remember, this coefficient of friction is between two surfaces. When you take out your clothes from your dresser, this surface here and the carpet, you didn't change any of that. The mu is constant. The mu did not change. But when you're taking items out of your dresser, the surface is pushing less on the dresser because the dresser doesn't weigh as much, right? The dresser isn't pushing down on the surface as much because you took out all your clothes. And so the normal force decreases. So if the normal force decreases and you're multiplying it with a constant mu, the force of friction will also decrease. And so if there's less force of friction involved, that means the object will be so much easier to move. So that is why you take items out of other items when you're trying to move it. Isn't that cool? Yeah, I think it's pretty cool. Now, let's say you just can't. You can't move the items inside of the dresser. You just can't. It's impossible. You wrapped it up with tape for whatever reason, but you need help. How can you move this? Right? So if you have like a moving partner, there's another way of reducing the normal force. And remember, the normal force is a surface force. And the surface can only push back on the object with however much force the object is pushing on the surface. And so this is what you do. Okay, well, I'll give you two scenarios. I'll give you a scenario of what you don't do and a scenario of what you do. So what you do not do is, if you're trying to push this dresser across the room and you have a partner there trying to help you out, you don't have your partner sitting or pushing down on the dresser, right? You don't push down on the dresser because that makes the dresser really hard to move. And you could try this with like a textbook, right? If you want to pull the textbook across, if you put your hand down and you're pushing down on the textbook as you're trying to move the book across the table, it's going to be harder to move. And that's because when you push down an object and the object's on the surface, the normal force increases. You're increasing the normal force. So here, you're increasing the normal force, so the force of friction would increase. Doesn't make any sense to do it if you're trying to move something. And so what your partner can do is, your partner can slightly lift the object off of the ground, and your partner lifts the object slightly off the ground, the normal force will decrease. And when the normal force decreases, we know that the force of friction, it also decreases. Now, this should make conceptual sense. Because if we were to go back to this, right? The idea of the atomic scale. When the ridges are on top of each other, it creates a lot of friction. But if you lift the ridges off of each other vertically, they can't rub against each other. The force of friction decreases. And so if you were to lift the object slightly off of the surface, that means the normal force would decrease. That would mean the force of friction would also decrease, thus making moving objects a lot easier. So if we were to go back here, right, in my Winter Wonderland scene, and I'm walking on ice, penguins do this, the way that the penguins walk, right? They kind of waddle side to side. When you're on ice, the best way to not slip is to exert more weight down on your foot that's stepping down, because you're pushing into the surface. You're increasing the normal force versus what it would normally do. Yeah. All right. Let's go over some misconceptions. If you take a look at your shoes, your kicks, your sneakers, on the bottom, I'm going to draw that's the bottom of my shoe, you'll notice that, when you're younger and you're on the playground and you just bought like a new set of shoes, and you're like, man, these new set of shoes, it's gonna make me this awesome basketball, kickball player, because look at the bottom of my shoes, they're new, they're brand new. Look at all these ridges. They're there. I'm gonna have so much grip. It's gonna be awesome. I'm gonna be the best player on the playground. False, young self. That's not the reason why we have these ridges. Well, and you're like, whoa, Mr. Lee. Hold on a second. Yes, those ridges, they do not increase grip or friction. Because if you look at it, force of friction is equal to mu times normal force. Where is the variable for grip? It's not there. It doesn't exist. There's no variable there that tells us that the number of grooves will increase friction. And you're like, hold on. But what about like when I wear my shoes for like a really long time and like the bottom of my shoes is like really bald, right? I slip a lot more like if I'm on the basketball court. Yes, that's true. That is very true. But that has nothing to do with this equation. Whoa, we'll get there in a second. The same thing with tires, okay? Tires. If your tires are bald, it looks like this. If your tires are not bald, we have these grooves there. Okay? Now, if you have bald tires and you drive on a surface that's wet, or if it's raining, you do this cool phenomena, terrifying phenomena. They called hydroplaning, where you basically become a boat at that point. Okay? And that same idea applies to these shoes. So if you have if we're driving, right, and we're driving on top of water, okay, and this is the same for shoes, right? So if we have, so this is my tire, and these are my shoes, okay. So I'm gonna zoom right there. That's my grip on my shoes, okay, and I'm stepping in a puddle. All right, I'm like trying to run across the puddle. Okay, now if you have plenty of these grooves, the reason why it has more grip, more friction, is because if we were to take a look at this equation, f of f is equal to mu times the normal force, you're not changing the mu. Okay, I'm gonna say that one more time. You're not changing the mu. So let's think about it. If we have these tires or these shoes, we have rubber on, I don't know, what is it, asphalt or concrete or whatever, right? We have rubber on asphalt, okay? When you drive on top of water, you still want rubber on asphalt because this has a super high mu. That's why we use these materials, okay? We have a super high mu. However, if your tires are bald or if you have shoes with no ridges, it becomes really slippery. And that's because it's no longer rubber on asphalt, but rather rubber on water. And rubber on water has low mu. Let me show you why. If your tires drive on top of the water, these ridges are designed so that the water fills in those ridges so that the tire can still make contact with the surface. Same here, okay? It fills in those ridges so that when you're stepping down on something, you're stepping down on the actual surface and not on water. So like what I mean by that is if you have flat tires, right? Or excuse me, bald tires, not flat tires. If you have bald tires and you drive on top of water, when you drive on top of water and the water doesn't have any place to go, it'll stay underneath the tire because the ridges aren't there to divert the water away. And that is true for the sneakers, right? If you have sneakers and you step on water and the water doesn't have any place to go, you're just stepping on water there. And it becomes really slippery. Okay, so if you watch basketball, or if you're a basketball player, you'll often notice they'll lick their hand and they'll like touch the bottom of their shoes. And that's not just because I don't know if basketball courts taste good, but when they do that, they're removing that layer of dust from the bottom of the shoes, and so they want rubber on. I don't know, what was it? They want rubber on court, whatever that court material is called, rather than dust on court. So they're removing that surface of dust when they lick their hands and they clean the bottom of their shoes. Anyways, ladies and gentlemen, this was Mr. Lee, and that was friction.